Good morning. I'm Altaf Hussain, a former professor, Department of Chemistry, University of Dhaka, Bangladesh. I have been teaching chemistry, and especially in final year undergrad X-ray crystallography and solid-state chemistry. That's what I taught about 25 years. Now, recently I retired, and I thought that I could probably prepare a series of lectures on that subject. And this is because almost all public university and university colleges, they have a compulsory 2 to 4 credits course on basic crystallography and solid-state chemistry or solid-state physics at the final year of undergraduate program. Though this course is a very important course, but a general feedback about the course that students are not very much comfortable, and the course teachers, according to student, are not satisfactorily teaching the course. There are many textbooks on this course and reference books too. In the website of International Union of Crystallography, here it is. One can get excellent materials on this course. Since I retired last December, I thought I can virtually give this course. But it is not always possible to give a course virtually unless and until you get a good number of students. I thought that I prepare some lecture, and even if I don't get enough students to participate in the course, I can upload a few of the lectures on the YouTube. We took a specific syllabus of a public university. There are about 7 chapters on this course, and this is a 2-credit course. The solid, crystal lattice, crystal symmetry, elementary crystal optics, X-ray diffraction and crystals, powder diffraction technique, single crystalline data collection, structures of solids. Each chapter has got subsections. I'll take one by one of these chapters and took all the subsections one by one too in every lectures or on chapters, as I mentioned. Well, start with solids. We know very well that we have lots of solid, and in a undergraduate level, first year undergraduate level, so what is solids? They do teach it. And now if I go for solid, it's one of the states of matter. Other two, gas and liquid. In solids, the molecules are tightly packed and having definite arrangement. Also, the molecules have fixed positions. The difference between liquid and solid state only that the molecules move around freely, and the movement restricted in solids. Specifically, it cannot move from its one position to another position. The solid molecules do vibrate in their positions. Well, if one increase the temperature of the solid or give heat energy to the solid, the vibrational motion increases. One more thing, that changing the temperature and pressure, one can convert one state to other state. This is what I saw. The solid has got the minimum energy, whereas liquid a little bit higher energy, and gas, most high energy, most highest energy. We can convert one to another. If we melt solid and form liquid, we call it is melting or fusion. So solid, by fusion or melting, we get liquid. If we vaporized it, we then get gas. It is reversible. If we want to get from gas to liquid, we condense it. And then if we want from liquid to solid, we freeze it. Now, if we go from solid straight to gas, we sublime it. And if we go from gas straight to solid, we call it deposition. You can see that we showed which one is endothermic process and which one is exothermic process. Well, now we go for classification of solids. Broadly, there are two classes of solid. One is amorphous, another is crystalline. Amorphous means that molecules in solids do not have any regular arrangement. Crystalline means that molecules in solid do have three-dimensional regular arrangement. So we call crystalline phases, and then we have mesophases. In crystalline phases, we have three-dimensional order, and mesophases, we have two-dimensional or one-dimensional order. If it is two-dimensional order, we call it symmetric. If we one-dimensional order, we call it nematic. These two, symmetric and nematic, are called liquid crystalline phase. And if we don't have any order, zero order, long range zero order, then we call it amorphous phase. Well, we can classify solids in other type also, depending on the bond type and also structure type. Solid, which you know that it is as hard as diamond, but also wax is a solid, it's as soft as wax. So we have a wide range of hardness in solids. Solid also do conduct electricity. Others do not conduct electricity. For example, diamond do not conduct electricity. We can manipulate the shapes of solid. Some are brittle and resistant to any change in shape. Some are malleable. That means we can change the shape. Physical properties and other things of solid do depend on its structure and bond types. Similarly, depending on bond and structure, we can classify solids more specifically. Then we can call metallic solid. In that we have metallic bonding. We can have ionic solid. We have ionic bonding. These what we have studied in the first year undergrad level. Metallic bonding, ionic bonding, and then covalent network bonding and molecular bonding. So these are the main types of solid. We can classify them. And then there are two other classes of solids which do not belong to other classification solid. That what we discussed a bit earlier. So these two other solids are called polymers and nanomaterials. Polymer solid, what happens? It's a chain of atoms, and the atoms in the chain are connected by covalent bonds, but atoms in between chains are attracted by intermolecular forces. Polymers do have very strong and high melting point molecule solid, and they are also flexible than that of metallic, ionic, and covalent network solids. Non-material solids are that the order of the size of the solid will be around 1 to 100 nanometer. A very interesting properties of nanomaterial solids are that its crystal size become nanocrystalline, and nanocrystalline has got very different properties than that of microcrystalline solids. We have very many techniques to characterize solid materials. And in this slide, I show that these are the different types of properties of solid. Or if we want to characterize, we have to determine these properties of the solids. But what are the techniques we use to characterize solid? You see, X-ray techniques, electron microscopic techniques, neutron diffraction techniques, optical microscopy, and lots of spectroscopical method. For example, infrared spectroscopy, UV visible spectroscopy, nuclear magnetic resonance spectroscopy, ESR spectroscopy, and many sorts of electron spectroscopy, here it is, and then X-ray spectroscopy, as well as Moosbaer spectroscopy. Though we have very many different techniques, but you can see here which one can properly characterize the particular properties of solid. Let's take X-ray diffraction. You see, we can characterize crystal structure, we can characterize unit cell space group, we can characterize whether it is amorphous or crystalline, and then phase identification. This is what we can do by X-ray crystallography. Other properties also we can do by X-ray crystallography, but then we have to supplement this by other techniques. It's not exactly we can characterize bond type and cellars of polycrystalline structure. We have to supplement with other techniques to characterize these properties. So electron microscopy technique, you see, this is one of the very important technique which can characterize almost all properties of solids. But then X-ray diffraction and electron diffraction, we do have a little bit difference, and we will study this while we are going for other chapter of the lecture series. But we see, if we say a few words on this, the X-ray diffraction, you can see in almost all laboratories of the world, they do have X-ray diffraction method. But electron diffraction and microscopy, these are rather costly instruments. So we do not get very much option of these technique to every laboratory. Therefore, electron diffraction technique, we have to have a better economic standard to run this electron diffraction and microscopic technique. Okay, I go to the next slide, and here we are comparing amorphous and crystalline solids. X-ray is one of the best techniques by which you can differentiate amorphous and crystalline solids. I believe almost all researchers take this technique to differentiate whether it is an amorphous or crystalline solid. I take an example, bismuth aluminum oxide. A reactant of this compound has been mixed and then heated. And we took the X-ray pattern of it. When it is heated at 250 degrees Celsius, you see there is a lump. This is what is intensity, and this is 2 theta. So 2 theta versus intensity, we record it in the X-ray pattern. So you can see a lump here. There is no sharp peak. You increase the temperature, and you see the same compound getting sharper and sharper and sharper peak. And here at 800 degrees Celsius, it is the highest crystallinity in it. But you can see how the crystals are developing with temperature. So X-ray diffraction, as I say, is one of the best technique to distinguish between distinguish or characterize crystalline solid. It is said that X-ray powder patterns of polycrystalline solids are their fingerprints. So it is an essential instrument for those who are working on solid. Okay, in this solid chapter, we have some terminology. One is isomorphism, another polymorphism, and another allotropic. So we have to know about this. I might not get, as we said, that I will have prepare a lecture for about 20 minutes or so. I'll stop when it is around 20 minutes and then continue in the next lecture. So isomorphism, what it is? If two compounds have identical structure, two compounds means the two chemical compositions are different than two different compounds, but they have identical structure. We refer this as isomorphism. That means if we get isomorphous compound, their morphologies are different. That is, their they have same morphologies. That is, they have same identical shapes. Another thing, we say isomorphism is that two different compounds, chemical compounds, have identical structure that we call isomorphous to each other. So identical structure means they will have same morphology, that is identical shape. Another important characteristic of isomorphous compounds that their empirical formula will have same atomic ratio. Same atomic ratio. In crystallography, what is said, isomorphous compound have identical symmetry, and also the atomic position are a set of parameters. That means we get unit cell parameters and fractional coordinates are almost same, but differ a little bit because of its atomic sizes. At molecular level, molecules are isomorphous if they and have similar shape. For example, isomorphous compounds do have these type of compounds, double sulfates. I write it like this, M1, M2, and I showed what is M1, what is M2. M1 is alkali metal, M2 a divalent ion of magnesium, manganese, iron, copper, etc. These form a series of isomorphous compounds. Similarly, alums, potassium, aluminium sulfate with 12 water molecules. These also form a series of isomorphous compounds. Spinels, magnesium, aluminium tetraoxide type compounds also have isomorphous compounds. Many coordination complexes. For example, here iron and aluminium, acetyl acetonato, iron, or acetyl acetonato, aluminium. They do also form solid solution like this. Very interesting that this isomorphous compound have different color. You see, iron is deep red, aluminium colorless. When they form solid solution, it is deep or pale pink color, depending on iron and aluminium ratio. We complete reasonably about isomorphism. Now we can take polymorphism. So here we have same compound having different structure. That's what we call polymorphous compounds. Same, the isomorphism is different compound having same structure, and polymorphism is same compound having different structure. So we will have same compounds, and same compounds can have different shape. Such compounds may also differ or have similar atomic ratio. Well, another important thing is that isomorphic and polymorphic compounds show different physical and chemical properties. And that can be characterized, as I say, by solid-state nuclear magnetic resonance, Raman spectra, X-ray spectroscopy, X-ray diffraction technique, thermal analysis. These are the techniques by which we characterize isomorphous compound and polymorphous compound. Isomorphous compound can also be classified. Polymorphous compound can also be classified depending on temperature and pressure. Two types of polymorphic compounds are monotropic polymorph. It has got a stable, one of the form is stable, and then it has a reasonable range of temperature and atmospheric pressure. That is, only one is stable, other one is not stable. Aneanthropic polymorph. This is a polymorph. One form is stable in one range of temperature and pressure. The other one is stable in another range of temperature and pressure. Example is carbamazepine and acetazolmide. Many inorganic and organic compounds exist as polymorphs. In minerals, the calcium carbonate and hydrous calcium carbonate has got polymorphous calcite, which is trigonal, and aragonite, which is orthorhombic. This is a classical example of polymorphs in minerals. But there are many minerals where we can get polymorphs. For example, in crystalline silicon, they have cristobalite, tetragonal, tridimite, triclinic quartz, trigonal. These are the polymorphs of crystallines. We can take an compound, organic compound, glycine. This is glycine. They have two polymorphs. One is hexagonal and another is monoclinic. We have very many binary metal oxides for chromium oxide, iron oxide, aluminum oxide. They form polymorphism. And we show it by Greek letters. One we can show as alpha phase, chromium dioxide alpha phase, which is tetragonal in shape, and beta phase, orthorhombic shape. In pharmaceutical compounds, we do have lots of polymorphism, and these are very much necessary that one polymorph is effective in therapeutical, another is not. So people prepare pharmaceutical compounds, polymorphs, and study the effectiveness of these compounds. With this, I finished the first lecture of the series of X-ray crystallography and solid state chemistry. We'll continue this by with the lecture 2. Hopefully, we share this lecture 2 within a week or so. Thank you very much.